Today, our topic is polarity in covalent bonds. Covalent bonds are formed by sharing of electron between two atoms. If the shared atoms are of same type, for example, O2, two oxygen atoms combine to give O2 molecule. And in this case, the electronegativity of two oxygen atoms are same. Therefore, the bonded electrons will not move towards any of the atom. That will be exactly shared. In such cases, there is no polarity. Polarity arises due to the shifting of electron pair towards any one of the atom. If the two atoms are of the same kind, for example, two oxygen atoms, two hydrogen atoms, two chlorine atoms, then the electron pair cannot move towards any of the atom because of the equal attraction from the two sides, or the electronegativity of the two bonded atoms are same. Such molecules are known as non-polar molecules, and the bond is known as non-polar covalent bond. But if the bonded atoms are different, for example, hydrogen and chlorine in HCl, or hydrogen and fluorine in HF, if the bonds are, if the atoms are different, then the electronegativity values also will be different. If one of the atom has more electronegativity than the other, it will attract the bonded pair of electrons towards that. Then what happens? The electron pair will be near to the more electronegative atom. So it will get a negative charge, a partial negative charge, not complete negative charge. If it is getting complete negative charge, it has to take the electron completely, one electron completely. But here, completely, it cannot take this electron. If it is taking completely, then it will change it to ionic bond. It is actually sharing. Covalent bond is sharing electron pair. Even though it is shared, it can attract the bonded pair of electron towards itself. So it will get a partial negative charge, and this one will get a partial positive charge. Such bonds are known as polar covalent bonds. So heteronuclear molecules like HF, the shared electron pair between the two atoms get displaced more towards fluorine, which is more electronegative. This results in polar covalent bond. Because of the development of partial charges, partial negative charge and partial positive charge, it will get a polar nature. So it is known as polar covalent bond. And this polar covalent can be observed in heteronuclear molecules. This polarity, what is the polarity in a molecule, can be measured in terms of dipole moment. Or we can compare the polarity in terms of dipole moment. Dipole moment is defined as the product of magnitude of the charge and the distance between the centers of positive and negative charge. So when we consider a bond, HF, for example, HF, in that bond, if one electron is completely transferred to fluorine, what is the charge developed on fluorine? That will be 1 unit negative charge, or accurately minus 96,500 coulombs. At the same time, if one electron completely transferred to fluorine, at the same time, what is the positive charge developed on the other side? Hydrogen, that will be plus 1, or accurately plus 96,500 coulombs. Not completely. If only 50% transferred to fluorine, what is the charge developed on fluorine? -1/2 units. At the same time on hydrogen, +1/2 units. So what is the charge developed on fluorine? Exactly the opposite charge will develop on hydrogen. Their magnitudes will be equal. Magnitudes are equal. That is why it is given in the equation charge. We have to consider only the magnitude of the charge. So dipole moment is equal to charge into distance of separation. That means distance between the nuclei of two bonded atoms. Charge into distance of separation R. That is dipole moment. So charge into distance of separation, that is known as dipole moment, and that can be used to measure the extent of polarization. How much the electrons are shifted. The same quantity can be used to compare the polarization in these molecules. And the unit of dipole moment, dBA. The symbol is capital D. When we measure it is charge coulombs into distance, meter, coulomb meter. How will you convert coulomb meter to dBA? It is the conversion factor. 1 dBA is equal to 3.33564 into 10 to -30 coulomb meter. So you will get the values in coulomb meter when you calculate, then divide it with the 3.33564 into 10 to -30. Then you will get the answer in dBA. Here C represents coulomb and M is meter. Then another important thing, the dipole moment of a molecule is the vector sum of the dipole moments of various bonds. Means dipole moment is a vector quantity. It depends on direction. It depends on direction. As the direction changes, the value will change. So dipole moment is a vector quantity. So dipole moment of a molecule is vector sum of dipole moments of each bonds. You can see some examples here. Here H2O, oxygen is more electronegative. Dipole moment is represented in this way, across arrow, pointing towards more electronegative atom. It is the direction of the dipole moment. The electrons will move towards oxygen. So it is in this direction and dipole moment of this bond in this direction. So vector sum will be in this direction as shown it is here. It is the resultant dipole moment. Sum of the dipole moments of these two bonds are in this direction. So H2O has a dipole moment. The reason it has a bent structure. Since the structure is bent, it has a resultant dipole moment. Now BeF2, beryllium difluoride. It is a linear molecule. So what happens? You listen. The dipole moment is in this direction. And here BeF dipole moment is in this direction. The two bonds are same. And the dipole moments are equal and opposite. So the net dipole moment is 0. So BeF2 is a non-polar molecule. It is very important. If the molecule is linear and the bonds are of the same kind, the dipole moments will be equal and opposite. Dipole moments will be equal and opposite, then it will cancel each other. Then the total dipole moment is 0. So we can consider this molecule as a non-polar molecule. A non-polar molecule. Here the atoms joined are different, but the net dipole moment is 0. So we can consider it as a non-polar molecule. Another example here, BF3. Fluorine is more electronegative. It is in this direction. The dipole moment in this direction. Here the dipole moment in this direction towards fluorine. The resultant dipole moment of these two bonds are in this direction. And this dipole moment will be cancelled by BF bond in the opposite direction. Here also the dipole moment is zero because the molecule is symmetric. Dipole moments of bonds will cancel each other. Dipole moments of bonds will cancel each other. Therefore, its dipole moment is zero. It is a non-polar molecule. Even though each bond has dipole moment, the total dipole moment of the molecule is zero because of the mutual cancellation of dipole moments. And therefore, this molecule is non-polar molecule. Now, some special cases, we can see some special cases. Here, dipole moment of NH3 is greater than that of NH3. Why? It is our question. Dipole moment of NH3 is greater than that of NF3. You know, when you compare nitrogen and hydrogen and nitrogen and fluorine, fluorine is the most electronegative element. Even then, dipole moment of NF3 is less than that of NH3. Why? What is the reason? Here you can see the structures of NH3 and NF3. It is NH3, NH, 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 NF, NF, NF. And this nitrogen has a lone pair in its molecule, a lone pair of electron, a pair of electron which is not involved in bonding. When we draw the Lewis structure, you may remember the lone pair of electron means electron pair which is not involved in the bonding. There is a pair of electron on nitrogen. So 3 into 2, 6 plus 2, 8. Thus it will get 8 electrons. So here there is a lone pair of electrons and a NF3, NF, a lone pair of electrons. So here, if there is lone pair, that lone pair has a dipole moment. That lone pair of electron has a dipole moment. Here you can see this, when you compare nitrogen and hydrogen, nitrogen is more electronegative, so dipole moment will be in this direction. Here dipole moment will be in this direction, dipole moment will be in this direction. So 3 dipole moments, you can see the 3 dipole moments and the resultant dipole moment in this direction represented using this blue crossed arrow. And the dipole moment of this lone pair also in the upward direction, in this direction. These two are in the same direction. So the resultant dipole moment will be a big value, such as 4.90 Newton raised to minus 3 coulomb meter. But here, fluorine is more electronegative, so dipole moments are in the opposite direction. And the resultant dipole moment also in the downward direction, represented using this blue curve. So these dipole moments, that is, they are opposite in direction, therefore the value reduces. 0.80 into 10 raised to minus 30 coulomb meter. So that is the reason. So if you are getting such a question, what you have to do, draw these two figures and represent the dipole moments of each bond and resultant dipole. After that, draw the dipole moment of lone pair. In this case also, do the same things. And here what you have to say, the resultant dipole moment and the dipole moment of lone pair are in the same direction. Here, the resultant dipole moment and the dipole moment of the lone pair are in opposite direction. Therefore, NH3 has higher dipole moment than NF3. That is the answer. And the next one, partial covalent character of ionic bond, Pajan's rule. So far we discussed the polarity of covalent bond. Covalent bond, we are not expecting any polarity, but because of the electronegativity difference, there is polarity. Similarly, in ionic bond, we are not expecting any covalent character because there is complete transfer of electron from one atom to the other. But even in ionic compounds, we can notice some covalent character. That is explained here. Then after giving the electron, for example, aluminum giving 3 electrons to another atom, for example, it is giving electrons to nitrogen to form aluminum nitride, AlN, giving 3 electrons to nitrogen. Then aluminum has 3 positive charge. 3 positive charge. Nitrogen has 3 negative charge. It will be very difficult to carry this 3 negative charge by nitrogen. Even though it is getting stability, the nucleus with only 7 positive charge has to attract this 10 electron. The attraction may not be effective. It is getting a stable configuration, but even then, nucleus has a limitation. But here, after giving this 3 electron, aluminum is in 3 plus positive charge. Even though it is getting stability, actually it will try to neutralize this 3 positive charge. So it will try to take its electron from nitrogen, but because of high electronegativity of nitrogen, it will not give it to aluminum, but at the same time, uh, because of this tug of war between aluminum and nitrogen, the electron pairs may shift slightly towards nitrogen, not completely. It cannot take it back completely, but the electron, it can attract the electron pair a little towards it. And this attracting power of positive ion, Al3+, that is known as polarizing power of cation. This attracting power of cation. It can attract electron cloud or electron pair, and its attracting power is known as polarizing power. And nitrogen, because of this huge negative charge, 3 negative charge, the nucleus cannot attract or cannot keep the electrons properly. That is why aluminum is attracting this electron pair. And because of the attraction of aluminum, if the electron pair is shifting slightly towards aluminum, there will be a polarizability. That will be polarized. Nitrogen will be polarized. One part near to aluminum, the electron density will be more. One part of the nitrogen, N3 minus. That means near the aluminum, the electron density will be more. Electrons will concentrate in that direction or in that part of it. That means the stable nitrogen will be polarized. Nitrogen will be polarized. One side, the electron density will be more. That is known as polarized situation, and that ability is known as polarizability. So the covalent character of ionic bond depends on 2 things: polarizing power of cation and polarizability of the anion. Is it clear? Now we can see the important points in Pajan's rule. From our discussion, it may be clear to you that as the positive charge on the cation increases, its polarizing power increases. As the charge on the cation increases, its polarizing power increases, and ionic character also will increase. At the same time, if the negative charge on the anion increases, if the negative charge on the anion increases, what happens? Polarizability of anion increases. Polarizability of anion increases. And as a result, ionic character of bond increases. Another factor is size. Aluminum is very small in size. The smaller the size of the cation and larger the size of the anion, the greater the covalent character of an ionic bond. The smaller the size of the cation, as the size of the cation decreases, it will attract the electron pair. So what happens? a type of sharing arises. Sharing. Even though it is completely donated the electron, because of the small size, its nucleus has a powerful attraction on this electron cloud. If the electrons are slightly moving towards the cation, a type of sharing arises. That is the covalent character. That sharing is the covalent character. So the smaller the size of the cation and larger the size of the anion, the greater the covalent character of the ionic bond. The greater the charge on the cation, Al3 plus, the greater the covalent character of the ionic bond. As the charge increases, it will attract the electron pair. A type of sharing arises. That means covalent character. The smaller the size of the cation and larger the size of the anion, the greater the covalent character of the ionic bond, the greater the charge on the cation, the greater the covalent character of the ionic bond. For cations of the same size and charge, the cations are of the same size and charge. The one with electronic configuration n-1 dn ns0, typical of transition metals, is more polarizing than the one with the noble gas configuration ns2 np6, typical of alkali and alkaline earth metal cations. So what we can conclude, transition metals are more polarizing than alkali metals and alkaline earth metals. What is the reason? Its size is smaller. Size of transition metals are smaller than alkali metals and alkaline earth metals. Therefore, the transition metal compounds has more covalent character. Transition metal compounds have more covalent character than alkali metal or alkaline earth metal compounds. Electronic configuration n-1 dn ns0, typical of transition, is more polarizing than the one with the noble gas configuration, typical of alkali and alkaline earth metal cations. Okay, it is Fajan's rule, and I think it is enough for today. And all of you study it well and write the notes. Okay.